We're excited also not only to be co-sponsoring with the library, but we're excited to have John here today. John Lindsey spoke to our branch and the community several years ago, but as we know, there's all kinds of things happening that change with the climate. So he's going to be presenting today on Mysteries of Our Climate. Great title, John. Thank you for that. And I've asked Edie Kerr to introduce John. Edie is a member of AAUW and has been helping with programs for years. And she suggested we invite John, and so she's done all the coordinating, and she's a very integral part of this particular educational program today. Thank you, Edie, for doing that. Hello, hello. Hi. Very glad to be here. Good afternoon. John is a meteorologist, and he's been in charge of corporate relations for PG&E and SLO until his recent retirement. So now he's going to move around and do things just like he's doing this afternoon, just good things throughout the world. And there's a lot to talk about because we've have so many questions about what is going to happen with us since our climate is introducing all these new events that we have to deal with, and he's going to help us to learn about that. But he is an environmental specialist. He has forecasted weather and oceanography conditions along the central coast of California for over 35 years now. And he monitors environmental radiation programs, emergency response organizations, and his forecast can be heard on every morning still, John?
I go on the radio every now and then, but not on a regular basis.
Okay, we'll miss you. Maybe we'll get a schedule and catch you. And he writes, he wrote, has written and still writes, and it appears in the Sunday edition of the San Luis Obispo Tribune and the Santa Maria Times. And he was writing for the San Ynez Valley News at Lompoc.
Yeah, they still publish it.
So,
yeah, Santa Maria Times have all those different papers, like in Lompoc.
Oh, yeah.
So it goes in that paper, it usually goes in all of them.
Okay, so we want everybody to know just what you're doing and what you're saying, what you're warning us about. And prior to working for PG&E, he was a marine meteorologist and research scientist with Tenera Environmental. He served in the Navy for over 24 years on search and rescue swimming, anti-submarine warfare technician, oceanography and weather, and so on. He was very embedded in this job. He attended Santa Rosa Junior College, California, and Cal Poly and SLO, and successfully completed the U.S. Naval Aviation Meteorology and Oceanography programs at the Naval Air Station in Pensacola, Florida. And he currently lives in Los Osos, California, with his wife Trish, who is with him today, and we're very happy to see her again. And he has two children who are have very interesting careers on the way. So, welcome, John. Thank you, and we look forward to hearing from you.
Oh, cool. All right. Can you all hear me right now? I've got a pretty loud voice, and it's really cool. Bill Tolman is here. You want to stand up, Bill? So Bill was in charge of Pacific Gas and Electric's Wave Connect program in Humboldt and also at Vandenberg Space Force Base. And he's currently at Vandenberg, and he's the lead on carbon-free energy. I guess that's the best way to describe it, Bill. Yeah. So if we have any questions, he's right here. So that's a wonderful resource right there. So the genesis of this, well, first I want to thank the AAUW. They got a really tremendous mission statement, and they do so much great work in our community. And also the city of Santa Maria for providing this wonderful facility and a brand new AV system. Look at that projector, isn't that pretty impressive, right? So the genesis of this was, if you looked at studies from Scripps and UC San Diego, since the 1970s, they indicate about a 13% increase in wave energy along our coastline. And I did the same study with our wave rider buoy, but it came out to be about the same, but it didn't explain why all the piers are failing up and down the coastline. Because if you're a marine engineer, you usually put about 150 to 300% safety margin in designing those piers and the pilings and the piers to withstand much more energy than what they anticipated. So I'd really kind of asked, what the heck is going on here? And what I discovered, if you took the top 20 wave events and just looked at those are the wave events that generally cause all the damage. Wave energy has gone up about 78%. And that to me makes a lot more sense than looking at the total average. So that's kind of the genesis behind my presentation today. So without further ado, this is a green flash, by the way. People think that's doesn't really exist, but it does. And in October, September seems to be the best months for green flash. But whenever you have offshore Santa Lucia winds blowing without much of a marine layer, right when the sun sets down, you'll often see a green flash. So it's not myth, it actually exists, right? All right, so with that I'll press on here. And, okay, I'll try it for you. Oh, here we go. Looks like we got a little issue here. I'll get this fixed in a heartbeat. That's probably why. There we go. Okay, so this was about a year and 2 months ago, and it was December of 2024, and so December 23rd of 2024, and this is up in Mavericks, up in Half Moon Bay. It's kind of famous for a big wave riding area, and the reason being is mostly because of the bottom topography. It tends to really elevate those long period waves. And 108 feet, probably the biggest wave I've ever heard of before in Mavericks. And it was Alo Savar was the person who rode this thing. I could not even imagine the courage it took to get on a wave that size. And renowned surfer Jeff Clarkson was probably stated the largest wave I've witnessed being ridden. And he's correct, and here's the proof, right? So here's a little video of what that actually looked like. And if you look at these waves, yeah, the height is impressive, but really the period is maybe the most impressive thing about this, the wavelength. And the longer the wavelength, the more energy a wave has. And probably an analogy that I utilize is that, you ever notice that you're standing on a corner and a car is coming towards you and it may have its stereo up full blast? The first thing you hear is the thump, thump, thump of the bass, right? And that's a longer period wave, longer period mechanical wave, because you're moving so much more energy underneath the sine wave. It takes a tremendous amount of energy to generate those long period waves. And they tend to propagate. You can see the little radar domes there at Half Moon Bay, right? So how he was able to do that is pretty remarkable. So to use an analogy again, you're standing on a corner, you're hearing the thump, thump, thump of the bass, the longer period waves, which propagate with very little loss. And not until that car is almost by you that you start hearing the mid-range and the treble. And that gets attenuated pretty darn quickly. So the longer period of the wave, the more energy it has on not a linear fashion, but exponentially more energy that it has. And Bill could probably talk about that with the Wave Connect program to generate electricity with ocean waves. So 3 types of waves. You have wind waves, and these waves have periods ranging from 1 to 30 plus seconds. wavelengths exceeding 2,500 feet in deep water and speeds over 55 miles per hour. However, the most common is about 25 miles per hour. So if you look at the charts, the surface charts across the Pacific Ocean, it's usually 600 nautical miles spacing. So at 25 miles per hour, usually it takes 1 day from the go to reach each 600 mile segment there. So it's easy to predict when the waves will arrive at your location. So it makes it really convenient. The other type of waves are seismic sea waves, tsunamis, and these have periods of between 10 to 20 minutes, and these waves have wavelengths exceeding 125 miles and can reach speeds up to 373, 435 miles per hour. So basically a jet airliner traveling across the Pacific, these tsunamis are traveling at about the same speed, a little bit slower, because they have such tremendously long wavelengths, all right? If you're out in the middle of the ocean and a tsunami was to pass, you wouldn't even notice it. It's when they start feeling the ocean bottom, and that's when, you know, boys like not conversation, but conserving energy. So what happens, the wavelength starts decreasing, but the wave height increases, all right, to make that you know, conserving that energy. The next one is tides, and these are extremely long wavelengths, as you can imagine. Usually along the Central Coast, we have 2 high tides and 2 low tides per day. So, you know, about a 6-hour period on tides, right? All right, and of course, they have to span nearly 13,000 miles, over 13, and they're about 550 miles per hour. But really, if you look at the tidal bulges, it's really the Earth rotating into those bulges, right? Ice them actually traveling. Now, peak wave height often corresponds with high tide. And I just thought that was so interesting. I had an indication that was the case, but then Scripps did a big study, and sure enough, it proved out to be true. They had a hypothesis, and it turned out to be fact. Okay, so with that said, how are waves generated? And the first thing you need winds, right? You need a storm. And where the winds blow over the water is called the fetch, which is right here. So basically, the stronger the winds, the higher the seas will become. And there's a ratio, it's 1 to 7. So when the wave height reaches the wave height reaches 1/7 of the wave length, it can no longer support itself and the wave crashes or breaks. And when it breaks, that generates even longer periods. So over time, with these waves crashing or breaking, the periods of the waves become longer and longer and longer. So that's why when you have these really strong winds, you generate these longer period waves, all right? Once the seas, now seas are locally generated in the fetch. Once the seas leave the fetch, there's no longer energy being introduced into them, they become swell. And some people call this ground swell. And that swell will propagate for thousands and thousands of miles. At least the long period swells will do that. Walter Monk, who was down at Scripps, who passed away a few years ago, I think he was 102 years old, pretty amazing guy. In 1963, he thought of a study to do, and his hypothesis was that all the different period waves would diminish at about the same amount. And his hypothesis turned out to be completely wrong. So he had a crew of scientists down, I believe, in Guam, a crew of scientists in Hawaii, some scientists in Japan, and some scientists up in Alaska, and also a wave measuring device in La Jolla. So what he did was he waited for the summer, when you had those huge storms in the southern hemisphere, and he had these crews of people with these wave measuring transducers, and what he found in 1963-64, that as these waves propagated across the Pacific Ocean, the shorter and medium periods part of the waves did diminish quite a bit, but the longer period waves just kept on trucking. So he's really astonished by that, right? So, and then our waverider buoys at Diablo Canyon, so that's why I put the forecast point, all right? And with these waves, you may have a wave train from the Gulf of Alaska, one from Japan, and maybe one from the Southern Hemisphere, plus locally generated seas. So you got a lot of different wave trains coming and converging at the same time often, if that makes sense. All right, So the factors in wave height and period is wind speed. Second one is how long the wind's been blowing over the fetch. And thirdly is the length of the wind fetch. There's some other factors here, such as, well, if you're up in the Gulf of Alaska, northern latitudes, and the air temperature is really cold, the air is much denser, and hence it could generate much higher waves by less dense, warmer air, right? So there's other factors here, but these are the top three. So with that being said, if you had a 20-knot wind blowing over a fetch of 200 nautical miles, the highest for 24 hours, the highest seas you would get only be 5 feet. That's as high as they'll ever get. If you have a 70-knot winds over 24 hours, the seas could get up to 56 feet. So you could really see that it's not a linear progression, but it exponentially grows, all right? That's why when you have tornadoes and hurricanes with winds over 70 or 80 or 100 miles per hour, it causes so much more damage. Let's say you had a 25 mile per hour wind and you went up to 50 miles per hour, the energy is not doubled, it exponentially increases. All right, does that make sense? That type of thing. That's why EVs, when you drive along the freeway, you know, electric vehicle could go almost twice its advertised range of 25 miles per hour, vice at 50 miles per hour. And when you start getting up to 80, 90 miles per hour, your range really diminishes so quickly because you're trying to battle the force of the air. All right, sort of makes sense? Okay. So on January 5th of 2023, and this is a tide gauge down at Port San Luis, and the blue line is the predicted tide height. And the green line is the actual wave height. And because of thermal expansion of the water column, we're seeing actual tides or actual sea level much higher than what was predicted. All right, so this is a very high tide. It was predicted to be 5.9 feet, which is a fairly significant high tide. In actuality, it was 6.9 feet, which is a really high tide. So, so basically, December 5th, 2025, and I'm going to talk a little bit about tides. This is just about a month and a half ago. We reached 7.4 feet in Los Osos. You see that whole parking lot there at Pasadena was flooded out. And then this was the day after New Year's Day, so it was earlier this month. The tide was 7.7 feet, which is one of the highest tides that we've ever seen before. And it completely flooded out the parking lot. And this is the little Baywood Pier. You can see the water was coming right up, almost submerging the pier, believe it or not. So the tide was predicted to be 6.9 feet, and it came in at 7.6 feet. So it was almost 9 inches higher than was predicted. And that's huge with these tides. It really makes a big difference. All right. So PG&E brought together a lot of climatologists and scientists trying to figure out what sea level will do over the years. And that's really important because a lot of the PG&E's infrastructure is actually built at sea level. I always remember Admiral Titley saying the Navy's really concerned about this because all the naval stations, right, all those ships are docked at sea level. So it's a major problem. And they decided to come up with this trend line, the black trend line. So basically, you know, by the year 2100, we're looking at sea levels around 47 inches higher than it was back in 2000, early 2000s. And so far, if you look right here at 2020, sea levels increased around 12 to 13 centimeters, which comes out to be a little bit over 5 inches. So this is proving to be true, right? And sea level increase is actually accelerating. It's not slowing down, but it's actually accelerating. You can kind of see that with these trend lines too. All right, so the largest sea level, the highest sea level we've ever seen at Port San Luis, we said 7.6 feet on the day after New Year's this year. Before that, the highest was 8 feet in March of 1983 when there was large storms coming in, El Nino storms got to 8 feet. But the highest sea level I ever saw was due to a tsunami. And it got up to basically 8.8 feet, which was right about here. And you could really notice those long wave periods with the tsunami, right? So I think why I bring this up, if you had, to say, high waves, high wind generated waves, with a high tide that was higher than normally predicted with storm surge and with storm runoff, and then all of a sudden you have a tsunami on top of that, I mean, my gosh, you're really looking at a really significant challenge for a lot of people on the coastline. All right, so we're talking about longer period waves. Once again, this is January of 2023, and this is a 20-second period wave, very long period wave. And look how this keeps on surging up the coastline. This is Pismo Beach, by the way. It just doesn't stop. It's like a little miniature tsunami, right? So that's why I keep harking at the notion, the longer period of the wave, the more energy, the more destruction it could do. All right, look at the poor little swing set there, really got battered on this. But that's a 20-second wave. So a little bit further up the coastline in Capitola, and this is during a big high tide, right? Remember I showed you how high the tide was? And just look at this, the downtown section really got hammered on this. And anybody been to Capitola Santa Cruz before? So a lot of you guys have been up there. January the 5th. And look at the whole downtown there. Because it was a high tide. I think it was like I said, it was 7.4 foot high tide. And you imagine what the destruction of this would be if the tide was actually over 8 feet. And that's not kind of what we're looking at in the future, right? Maybe up to 9 feet or so. And Trisha's sister lives up in right there, which is called West Cliff. And that road was a 1-lane road for a long time. They finally they opened up to 2 lanes. All right, so what's causing this? And storms, okay, so I better point this out. California is right here. This is the Alaska, this is the Aleutian chain, this is the Gulf of Alaska, the Pacific Ocean. Storms are just becoming more intense. The pressures in them are dropping off. And the reason being is because there's a release of latent heat. And you ever notice before it rains or before it snows, it gets warmer? Ever seen that before? So that's the release of latent heat. So when that water vapor condenses is a warming process. The opposite of that is evaporation. And you'll know that if you ever go outside on a windy day with wet clothes. I mean, you'll just freeze immediately, right? The opposite of that is condensation. So what happens is that when you have greater amounts of condensation, it's a warming process, you release more latent heat, that air masses ascends, and the pressure, the central pressures in those storms become lower and lower and lower. And nature never likes anything out of balance. So put it this way, if you have a tire and you remove the valve stem, and let's say the pressure in that tire was only 2 psi, you'll get some air coming out, but it won't be that strong. If that tire is inflated up to 35 or 36 psi, per square inch, and you open up that valve, I mean, the air is just screaming out of that thing, right? And the same thing can be said for these storms. The lower the pressure, especially near an area of high pressure, the stronger the winds will become. And at our latitude, if you look at this, you pop over here, I never ever thought that we would see pressure this low in latitude at 941 millibars. That just surprised the heck out of me. And this occurred on December 22nd of 2024. And these winds are probably maybe 110, 115 miles per hour is what I estimated them to be. So well beyond hurricane force, right? I mean, so they generated some huge waves. Now we were lucky because, 14 months ago, look at the tides. The tides were only, basically the actual tide was actually below the predicted tide. It was only 2.3 feet. We were so lucky that we didn't have a 5 or 6 or 7 foot tide when this wave event arrived along the coastline. But despite being such a low tide, this is the end of the Santa Cruz Boardwalk Pier. And it literally took the end of that pier off. And you can see the little case crawler here, and the bathrooms went. It was just unbelievable. Like, there's the bathrooms right there washing up on the beach, you know? And I just blew me away when I saw this. And even Cayucas, you know, I went down to the Harmony Headlands and took some photographs. But this is during the wave trough, and you know, this is a big pier, and look how the water's coming up on that thing. And it damaged the end pilings here. And that's a brand new pier, for crying out loud, that was supposed to withstand the biggest wave events, you know, for the next 100 years or so. And it didn't do that. And of course, is that famous little shipwreck, that fishing boat off the Harmony Headlands. So, how do we measure waves? We use wave rider buoys. And this particular station has been in operation since June of 1983. And these wave rider buoys have about 84 dry cells, batteries in them. So about every 18 months, we have to take the old buoy back, drag out the new buoy, install it, take the old buoy back and put new coatings on it, do a calibration on it, and replace the dry cells. So pretty fun job. I really love this job. And the mooring system on it looks like this. So this is off the Diablo Canyon Power Plant, about 80 feet of water or so. And at the bottom, the mooring's actually we took a railroad wheel off a train, weighs I think 774 pounds. And then we wrapped a chain around that railroad wheel, and that goes up to a couple of bungees that are able to stretch 3 times their normal length. And one of the more enjoyable aspects of my job was to dive on that mooring system. Because it was so deep, we were limited to bottom time, because if you stayed down too long, you would start getting all the nitrogen building up in your blood, in your plasma, right? So you couldn't stand. So we went down there with a crew, and everybody had their own little job to do, and it was really fun. So anyway, this is what the mooring system looks like. And remember I talked about how at a forecast point, you have a whole bunch of different wave trains coming in. You know, it could be from the Gulf of Alaska, local generated seas, from the southern hemisphere, who knows? But there's a lot of different wave trains. Even hurricane swells coming from from Baja California will come up, and you can kind of recognize them. So what we do is we have what's called a spectrum analysis, and we divide the amounts of energy in each spectral band. So here's the really short periods from 2 to 6 seconds, going all the way up to 22 plus seconds. Now, if you went out there with a stopwatch during a big wave event, you can actually measure wave periods of 30 to 35 seconds. But because the accelerometers in these wave rider buoys can't really detect those really long periods, but they're there, all right? So normally speaking, when you look at the spectrum analysis, in the 22 plus seconds, you only got 1 centimeter square. That's usually what you see when you look at the wave rider buoy data. And this wave rider buoy data is available to everybody. It's on what's called the script site, CDIP, all right? You can see it. So back in 2016, I noticed that we got up to 2657 from a big storm in the Gulf of Alaska. And this is the most I've ever saw before, and I thought, oh, we'll never get to that level again. And then in 2021, January the 10th, we actually exceeded that at 2728. I never thought we'd see energy like that. And when I was at the Harmony Headlands about 14 months ago, I saw this, 7159. And I thought, oh, this stupid wave rider buoy, it's not functioning, it's not in calibration, right? So what I did, I went immediately on the Scripps network and looked at all the other wave rider buoys up and down our coastline, and they were indicating the exact same thing. So huge amounts of energy. So what I did, I took the 20 top wave events, and the December 23rd wave event only got, well, it's high, I mean it was 19.8, but we've had larger and higher wave heights. So if you just went by the wave height, 19.78 feet, there's quite a few other wave events that are much higher than that, right? A little bit higher than that. But look at that period. So I said, oh, that's interesting. So what I did was I used this equation, Hillard's wave formula, and so you have specific weight of water, which is 64 pounds per cubic foot. You have wavelength in feet. You have wave height in feet. I know I'm stuck in the English system. So often I'm mixing units up a lot, like from the English system to the metric system. It's just, you know, I went to the nutrition class on Wednesday, and they finally went from pounds to kilograms. You know, I thought it was kind of interesting. But anyway, there you go. So since the wave runner buoy is in 80 feet of water, what happens is that as the waves start filling the bottom in 1/2 of their wavelength, they start slowing down, but the wave height starts increasing. And so I used 80 feet of water, and this is a 22-second wave, has a wavelength of 2,500 feet in deep water, but about 1,100 feet in shallower water. And that's why at Mavericks, that wave was so incredibly high. All right? So when you run the data through that formula, you can see that last year's wave event, 14 months ago, even though the wave height wasn't the highest, the energy was about 3.5 million pounds. All right? And when you chart this out and you do a trend line, that's where we come up with the 78% rise in wave energy, all right, in foot-pounds. Does this sort of make sense? And I'm concerned about this is because, you know, we spend a lot of money in our piers and our coastal structures and whatnot, and you know, I don't know, with the electeds and the policymakers, I think we're gonna have to make structures a lot more resilient, right, to stand up to this punishment. And the thing to remember is that this isn't every year. I mean, some years you have a lot less energy, like so far this year's been pretty calm, and then other years it really spikes. So, I don't know, it's almost like the frog in the water pot. You know, people expect this to happen every year, but we may go 2 or 3 years without a big wave event, and then bam, all of a sudden we've got the biggest wave we've ever seen before, the most energetic wave we've ever seen before. So just keep that in mind, right? But this trend line to me is extremely significant, to say the least. All right, so what's causing this? As I said, a warming atmosphere can hold more water vapor, simple law of physics, can't argue against that. Greater latent heat release, and then produces stronger storms, which means lower pressures, which means stronger winds blowing over the fence, generating higher waves. All right? So, how do we know what's gone on in the past? And we could use corals, we could use tree rings, but probably the best way is looking at ice core samples. And go back around 50,000 years in Greenland core samples, go back, my gosh, 600,000 years in Antarctica and figure out what's going on. What happens is there's actual bubbles of the atmosphere trapped in bubbles in these ice layers. So you go back and you look at the CO2 levels, you can actually look at what the temperature was, but there's some isotopes of oxygen, you can make a correlation that way. So it's really, really fascinating. So what we found is that CO2 levels never gone beyond 300 parts per million, or 600,000 years. But if you look, there is this 100,000 year cycle, right? That's natural climate change. But look at lately, it's beyond hockey stick. And that's what really, I've always been a skeptic. I always love being a skeptic. You gotta be that way if you're, you know, in the science. But to see this much change over this little time, that really convinced me that we're causing this, all right? Downloaded this graph. It was only about 400 parts per million, but currently, and I downloaded this about a year ago, we're at 425 parts per million. So that's pretty significant. You know, if you have a commercial driver's license, for us without a commercial license, you can get busted for a DUI, driving under the influence, with 0.08 alcohol content, which is, you know, basically 800 parts per million. If you have a commercial driver's license, it's only 400 parts per million. So I guess you could say the atmosphere would be guilty of a DUI right now at this point, right? All right. So these are natural variations, and the biggest one, remember I showed you the 100,000 year cycle? You know, and you can see it right here, 100,000 years. Really beautifully done. That's because the Earth's orbit around the sun is not a perfect circle, it's really an eclipse. And this causes climate change, but over 100,000 years, right? And then you have axial tilt, and that's about a 41,000 year cycle. And just, you know, we're seeing that the axis of the Earth just move a little bit. Currently it's 23.5 degrees. And then you also have the Earth sort of wobbles on its axis. That's about a 23,000 year cycle. So these, I think the point I want to make, these are very long cycles and they do contribute to climate change, but can't justify what's going on lately, all right? Is it the sun? And this is global temperatures, or this is global temperatures right here on this line, and this is the output from the sun. And you can see there's not enough forcing to justify what's going on with global temperatures. And this is 1880. We use that date because that was kind of the start of the Industrial Revolution, all right? Is it the Earth's orbit? And yeah, if I went back 100,000 years, you would see a forcing here. But since 1880, that doesn't justify the increase in air temperature. Is it volcanoes? And yeah, volcanoes really spill out a lot of CO2 in the atmosphere. They also throw out basically a lot of aerosols that actually reflect a lot of the sun's energy back into space. So it's a bit of a wash. Is it all three? And nah, I mean, you just see there's not enough forcing to justify the way temperatures are increasing. Back on my birthday in 2020, San Luis Obispo hit 120 degrees and Salt Lake 121 degrees. And somebody told me we'd hit those temperatures, I would never have believed them, right? So Sean, I, and Trish went out to the airport and we had a little handheld, weather monitor, right? And at the airport it was 117 degrees when we went out there. So smashed all the records, needless to say. As you can see, the global temperatures just keep on rising. They tend to be lower during La Nina conditions and warmer during El Nino. So 2023 was the warmest record, the warmest year on record, and it came down a little bit in 24 and 25. But it looks like we'll be heading back into another El Nino cycle at the end of this year. So we'll probably see more record-breaking temperatures. Since 1880 to today, this is the average temperature per month from, clockwise from January to December. And you can really see how temperatures have gradually increased since the Industrial Revolution. Once again, the rate of change is so quick. It's nothing that we've ever seen before. I guess what's it, 24? Take a look at this. Yeah, pretty major increase on that. Air temperature change. So once again, PG&E is recommending this line, which basically means that by 2100, average temperatures will be probably about 6 degrees warmer than they are today on average, which is wild. I mean, that's almost hard to comprehend, and so far we're actually a bit ahead of this trend line, unfortunately. Sea level increase, we talked about that. I love this slide because it really shows that most of the Earth is covered by the ocean, and unfortunately, most of the excess heat is going into the ocean as we speak. And so ocean temperatures, they keep rising. 2023, once again, was the warmest year on record, and that's because we're basically in a La Nina right now. When sea ice melts, it doesn't do anything as far as increasing sea level. Ice is one of those miraculous molecules that when it freezes, it actually expands. And a lot of people hypothesize that's why life on Earth is actually possible because of that effect. However, when you have melting land ice, that increases sea level, and also when you have iceberg capping, that's increasing sea level. Most of the sea level increase that we've seen lately has been thermal expansion of the water column. The ocean's getting warmer and warmer. And as I said before, by 2100, we're looking at about 47 inches of sea level increase. All right, and I really love this one, sea level change. And yeah, you can see it just really increasing, and just a few inches makes a huge difference. It really, you know, from a 7.2 foot high tide to a 7.6 foot high tide, makes all the difference in the world. You can really see this coming up. So basically about 12 to 13 centimeters of increase, which is about 5.5 inches or so. More U.S. downpours when it does rain. Rainfall is becoming more intense because there's more water vapor in the atmosphere to condense, producing periods of more intense rainfall. But we should be proud of the Central Coast. You know, Bill should be proud of what he's doing. Between Diablo Canyon and Topaz Solar Farm out there in the Carrizo Plains, the Central Coast exports more clean energy than any other region in the United States. So we actually, we supply so much power to the Western grid, much more than we consume, believe it or not. So we should be all, you know, thankful for that. And now I took this picture on Wednesday of jellyfish clouds at sunrise. I thought it was really cool. So there you go. You know, I'm sorry, I should have asked, does anybody have any questions? I was going to ask questions as I went along, and yeah, it's a lot better.
What effect is it going to have when they close Diablo Canyon, which is imminent?
Well, they got a 5-year extension, right? They were, in fact, the power plant was supposed to close last year, 2025, I believe. I think, memory serves me right, I think Unit 1 was supposed to close down in 24, and then Unit 2 in 2025, I think, if I remember right. And here, both units are humming away just fine. So the state gave us, or gave Diablo Canyon a 5-year extension. Diablo Canyon's going for a 20-year extension because that's what the NRC, the Nuclear Regulatory Commission, requires, 20 years. So I'm hoping, and I'm sure a lot of employees at Diablo Canyon are hoping that they'll go for another 20 years. I just love that question. I think one of the aspects about this was that these AI data centers are going in everywhere. And some of these AI data centers have a load of 550 megawatts. And to put that in perspective, that's almost a quarter of Diablo Canyon's output. Can you imagine that? 1 megawatt can safely supply 1,000 homes. And here, these data centers they want 550 megawatts. It's incredible. And in fact, in Northern Virginia, they're putting in so many data centers that the Eastern Grid operators saying, look, we can't supply power to you anymore. You have to come up with your own power sources to do this. So it's a real gold rush. So I think because the power plant's built, it emits very little the greenhouse gases. And with these AI data centers, I think it's going to go for a full 20 years. But that's just my humble little opinion. You know, I don't know what's actually going to transpire. So there you go. Also, there's a lot of companies now that want to use the spent fuel from Diablo Canyon to make these smaller modular reactors. And I think maybe Bill has some input on that, but it's, yeah, we'll see what happens, right? I think it's really fascinating. So great question. There's another question back here. Oh, right there. I'll get there. The lady in the teal or blue. There you go.
You don't, or have you studied water temperature in relation to any of these activities with the wave?
Oh yeah, water temperatures unfortunately is in fact I've got a control on here. Yeah, the graph I kind of went fast on here. At least I think I did. Yeah, there you go. So you can see, you know, each year represents 1 year, and you can see that like globally, ocean temperatures highest on record daily average sea surface temperatures since 1979 to 23 have really been increasing. One interesting thing about our coastline though is that you have a static low, not a dynamic low, but a static low pressure system that develops over the Central Valley of California. And that's due because it just gets so bloody hot, right? I mean, just ask anybody from Bakersfield or Fresno or Hanford how hot it gets. Because it gets so hot, the air expands and it creates an area of low pressure over the Central Valley. However, the Eastern Pacific high off the California coastline remains the same. Nature never likes anything out of balance, so the northwesterly winds are becoming stronger along our coastline, and hence, as those stronger winds mix out the temperature inversion layer, we're seeing more and more sunny days, less days of foggy, overcast conditions, and it's also producing more upwelling. It's increasing the amount of upwelling. We're bringing this cold, deep, deuterish water up to the surface. So along our coastline, seawater temperatures haven't really increased at all. They've stayed pretty much the same because of increasing northwesterly winds, which has been great for the ecosystem, right? However, when those northwesterly winds relax, which they often do, that's when we're seeing the warmer seawater temperatures along our coastline. But other regions of the world it's just getting warmer and warmer all the time. So they're great question. The lady in the back.
Access tilt, it said something about 41,000.
Exactly. And you go back to that slide. Am I going in the right direction? Oh, wait. Yeah, I'm in the right direction. Here we go. Yeah, axle tilt about 41,000 years.
What does that mean?
Basically, we're 23.5 degrees. The tilt changes just ever so slightly every 41,000 years, gradually, and that contributes to natural climate change. So great memory. You know that. Yes.
I have a question. I have a weather observation I'd like you to comment on.
Yeah.
I dread winters, so I've always watched liquid amber.
Okay.
They haven't turned this year. They haven't lost their leaves. What is? We had a cold, warm winter.
Yeah. What's liquid amber again?
It's the trees right out
Oh, the
there.
trees.
Deciduous.
Yeah. You know, well.
They aren't losing their leaves.
Well, this past December was like the second warmest December on record.
Is that it?
Easily, yeah. It was really warm this last December. I'm kind of becoming a birder in Mortal Bay because it's really fun. I take a lot of photographs of birds. We're seeing brant geese that usually migrate up to the Gulf of Alaska to eat eelgrass during the summer, and then they migrate back south during the winter. Some of these, we got one brant we call him Brian the Brant. There's like the heck with it. We're just staying here in Mortal Bay year round. We don't have to go up to Alaska anymore.
Well, usually these trees I watch,
Yeah.
it tells me winter's coming. I don't like it. Start turning in September.
Yeah, no, that's a direct result. I mean, to look at cherry blossom, I had a slide here once on the cherry blossoms in Japan. Yeah, cherry blossoms a big deal in Japan, right? When they blossom, they're earlier and earlier and earlier almost every year. The blossoms are happening earlier and earlier each year. Also got a help with a study at Cal Poly that looked at rattlesnakes at Indio and Montana Duro State Park. And they kind of go in semi-hibernation, and all these years of studies, they catch them, they put a little electronic tag on them, and then they study their movements and what they do, is that these rattlesnakes are coming out earlier and earlier every year to look for a mate. So yeah, and then you look at disease, different types of mosquitoes and diseases they carry are just making their way farther northward. And then look at viticulture. A lot of these viticulturalists are buying property up in Oregon and Washington. Either you move up or you move north, right? So yeah, there's a lot of implications here. Along the Central Coast, because of these stronger and stronger northwesterly winds, we haven't had the big temperature increase like other parts of the country have. If you go on the other side of the transverse range, you get the sundowner winds. Santa Barbara's had a significant increase in air temperature, on average. So yeah, so there you go. Yes?
I have a question about the local climate.
Yeah.
The cliff swallows, they torture me every year, starting in February.
The what?
The cliff swallows,
Oh, yeah, sure.
they come, they
Yeah.
try to nest,
Mhm.
and chase them down, watch their little homes off.
Yeah.
It doesn't happen every year. So what's your prediction for next month?
Oh, that's probably as difficult as, so usually at Diablo, they always arrive in March.
They were horrible last year.
Yeah, it probably depends on, you know, the whole food web and how many, you know, flies they could catch or insects on the wing they could catch.
Uh-huh.
It's probably kind of like trying to predict the monarch butterflies, right?
Yeah.
So I know at Diablo, like around like San Juan Capistrano, the swans always return, right? And at Diablo is always like March the 10th. They always
The
show
monarchs
up.
don't build nests in my house.
Oh, I know. They're not. They mess up everything. But yeah, I don't know. I can honestly say I'm not really sure about
And they're
that.
very clever. I got rid of them on one side, so they started building on the other
Oh
side.
yeah. It's fun to see them over or building nests underneath underpasses, right?
Oh, springtime.
Yeah, all over the place. All right, we have a question back here, sir.
What would you say would be the 5 biggest things that we, our children, and our grandchildren can do to help circumvent global climate change?
Yeah, well, I mean, obviously, well, the biggest bang for the buck is always energy efficiency, right? That's always your biggest bang for the buck. But I mean, a lot of that's been captured. Remember that when everybody had incandescent light bulbs and we want everybody to go to light emitting diodes, and everybody was all up in arms, I'll never get rid of my incandescent light bulb, and people finally went to LEDs, and you know, the light's better, they last forever, people don't have to climb up on ladders and replace them every year, every 6 months. And basically, when you replace an LED, it's probably good for the rest of your life, right? So I think energy efficiency is really crucial. Trish and I, we got solar panels on our house, and we have 2 EVs. And essentially, we don't pay a PG&E bill any longer, despite having 2 EVs. So, in fact, there's a company called Donut Battery. I don't know if it's Viperware, if it's really serious, but they've developed a solid state battery that supposedly will be good for 1 million miles. So what they're saying is that when you buy a new car, you'll keep the battery pack, but you'll just plug it into a new car and drive it for like 250,000 miles. But also for energy storage, it could be really huge. So that's on the, we'll see if it pans out or not, right? So that's what I do. I think people also say what you eat makes a big difference. I love going to the farmers markets because, you know, all the produce is produced pretty nearby, so you don't have to truck it all those miles, right? That adds a lot of CO2 to the atmosphere. And then Bill is really on the cutting edge of carbon-free energy sources. That's what he's doing at Vandenberg Space Force Base. So yeah, you want to comment about that, Bill? Some of the things that you're doing with carbon-free energy?
So Vandenberg Space Force Base is down the coast here. I live in Santa Maria, so I have a shorter commute than when I lived in Los Osos.
Yeah.
It's 100% solar power in the daytime. We have 160 acres of photovoltaic panels powering the base. We're right now in the middle of procuring batteries, very large batteries, industrial batteries, to help store more of the solar energy produced in the daytime to allow us to use that very cheap solar energy at night instead of the very expensive PG&E power. And then we're right now working with the Pentagon on a program for geothermal energy. So it turns out that like Morro Rock at Morro Bay, which is a volcanic remnant, there is a similar volcanic remnant called Tranquilla Mountain at Vandenberg.
Really?
And the U.S. Geological Survey has identified Vandenberg as being the top geothermal energy resource of any Air Force base in the country.
Oh, cool. And I grew up in Santa Rosa, and up in Sonoma County, Lake County, you know, we have the geysers, right? And that's I think probably one of the biggest geothermal generation areas
It
anywhere.
is.
Yeah, so, yeah, that's really cool, Bill. I have some good answers there. Any other, yes, sir?
What's the status of carbon capture?
Well, I was gonna bring that up. And, that was one of the other big things I was gonna mention. That may be the only way to really, one of the ways to fix this. And to be really honest with you, I don't know much about it at this point, what's going on. I mean, well, I should correct myself. Farming practices, right? Right now, we till the earth and we use fertilizer and pesticides, but they've really found out through non-till practices and preserving a lot of the plant life, they're able to capture a lot of carbon in the soil doing that, right? So that I think farming practices will be a big deal in the future, because you could really capture a lot of carbon with correct farming practices and not have to use as much fertilizer or as much pesticide. You know, I knew a guy, Bob Blanchard, who actually managed the North Diablo Canyon lands, did a great job with what's called managed grazing and whatnot. He has a ranch up in Cayugas called Old Creek Ranch. And what he did was he raises oranges and avocados. And he got himself a whole bunch of chickens to control pests. So the chickens are organic, right? They eat all the pests, and they also fertilize all these trees. So he doesn't have to fertilize them anymore. And he's got all these chickens controlling all the pests. So now his farm is certified organic, and he sells his eggs up in Palo Alto and Santa Cruz, for $15 or $20 a dozen. He also sells organic orange juice. So that's another, I'm saying for ag, that might be a big one there. So that's my answer anyway. Yes, in the back.
One contribution here, ducks eat snails better than chickens.
Oh, well, there you go.
And they're better on your vegetables too, they're not as bad. But, there was something else I wanted to say about, but it left me, and maybe I'll get back to it in a minute.
Yeah, I love ducks. I think Trish had some ducks. Yeah, they're awesome. Yes, sir.
So we have all of these different ways of preventing carbon dioxide to go in the atmosphere. Are we ever gonna really get it under control?
Oh, I know.
Well, you know, the thing is, battery technology and renewable energy sources are becoming cheaper and cheaper as we go on. So it made us boil it down to economics, right? A guy I worked with, Chuck Belmont at the Obligate, always told me that all energy migrates to the lowest BTU, the cost of Brutus thermal units. And I think we're at a point where, look at me, for example, and Trish, that I have an Equinox, and it's 100% electric. Trish has a 4xe, a Jeep Wrangler 4xe. So with Trish, she's able to drive these short trips because her work is pretty nearby, and she hardly uses no gas. And we rather use electricity because it's a hell of a lot cheaper than buying gas, right? So I think economics are going to drive that. Where right now petroleum is pretty cheap. It's so important. Petroleum's used in everything, and I always wonder why it's kind of a sin to burn it. We should keep it, using it for manufacturing everything, right? But all these cycles, right? So the oil market crashes and all these rigs shut down, right? And then all of a sudden the oil gets up to $100, $150, $160 per barrel, and gas goes through the roof, and everybody goes to EVs. So it's really economics I think is going to drive this more than anything else. So that's my answer on
So
that
it's really,
one.
it's a global thing, no, it's not just.
Oh, I know. Yeah,
Coast here.
but I think as you know, the price for solar panels have really decreased, and I think the price for batteries have been going down. So I think those aspects basically, you know, would really help in burning less fossil fuels and using more solar. I guess you can make the argument though that fossil fuels are solar, right? It's just stored in a different way because photosynthesis produce those fossil fuels, and then somewhere down the road, bacteria and fungi learned how to eat those, so then no more fossil fuels were being developed, right? Because bacteria started to eat them. Really, really interesting, you think about it. But anyway, there you go. And like Bill says, there's geothermal too, so who knows?
I
Yes.
remember. I
Yeah.
don't think we're gonna have to worry about global warming or any of that, because, I belong to a science group that does a Zoom from the Bay Area.
Yeah.
We talked about PFAS in our diet, in our liver, in our kidneys, in our everything, the water, and it doesn't leave our bodies.
Oh, you like microplastics?
Yes.
Yeah, oh, who knows? I mean, I'm not
So-
a doctor, but it can't be good, put it that
No.
way, so.
Well, there's some very interesting things happening with studies, and one of the problems with the petroleum industry and the PFAS
Yeah.
is that once something is illegal and they've decided it's wrong, they change the chemical by one little tiny molecule and put it back into our environment.
Well, that's unfortunate, that's the case, you know? Yeah, there you go. But all I wanted to do today was just kind of give you the facts, right? Yeah, so there you go.
Thank
I'm
you.
not an expert on macroplastics. Bill?
What's going on with the Central Valley tule fogs? We've had a winter
Yeah.
of just
Horrific, huh? Well, you know, this year was supposed to have below average rainfall, but we've had those 3 Madeline Julian oscillations, you know, from the southwestern Pacific come up and produce all that moisture off the Mexican coast. Usually when the storm track is way up north, we have a pretty severe drought, which means there's no winds. And you have to have winds to mix out that temperature and inversion layer to get rid of that tule fog. And it's just been opposite. We've had some rain to moisten that ground, but then very little in the way of winds. And bam, you just got days and days. You know, I looked at Hanford, which is the National Weather Service station there in San Joaquin Valley. And in December, there were days where the temperature only varied 2 degrees throughout the whole day. It was like 41 degrees at night and like 43 degrees during the day. Yeah, that's crazy. Yeah, but that's why the lack of storms, lack of those cold fronts coming down the coastline, there's nothing to mix out that inversion layer. So you could have 40-degree temperatures within that inversion layer on the ground, and it could be up to 80 degrees above it. So a 40-degree temperature differential, this 15 or 20 feet. Yes?
What about the snows or lack of snow in the Sierras
Yeah.
impacting on our
Yeah.
water supply?
Well, when snow falls when its precipitation falls as snow, that's great because that's a reservoir. It slowly melts in the spring and early summer, and it not only does it provide water, it generates a lot of electricity, right? PG&E is one of the world's largest hydroelectric network anywhere in the world. And unfortunately, the snow level's been gradually increasing, right? It's rising up in elevation. And of course, you're losing that solid reservoir, right? As snow levels get higher and higher, there's less snow to melt to provide water for us and also to generate electricity. So it's a double whammy. And then you factor in all the regs for the fish, right? Because you got to have certain water temperatures in a lot of our streams and rivers, and they achieve those lower temperatures by releasing more water. But then you don't want to release too much because you'll dry up those reservoirs and you won't have water for agriculture and for people, and then of course to generate electricity. So it's definitely that's another challenge with climate change. So thanks for bringing that up. Yeah, you know, Helms Pump Storage Facility was built in partnership with Diablo Canyon. So way back when, at night, we would pump water up the hill, and then between Courtright Reservoir and Washoe Lake, and then during the day, we let the water run down the hill to generate electricity. But now, because there's so much solar energy out there, we're seeing something called the duck curve. And so what happens when the sun sets and people turn on their big screen TVs and they start preparing dinner, that's when you know, there's a real spike in energy consumption. So it's pretty fascinating. So Helms is kind of operating at a different schedule than he used to many, many years ago. So anyway, there you go. It's 2:15. I'm kind of all talked out. And Trish and I